Hello, my name is Olusegun. I'm an electrical engineer and a data science enthusiast, and I volunteering with Statistics Without Borders. In this module, for this lesson under the subject of biostatistics, we'll be discussing the binomial distribution. From the name bi, you can see it involves two things, the distribution that involves two terms, and we'll get clearer on what it really means as we progress through the module. Now, in the agenda for this module, we'll first start off by discussing the Bernoulli trial and the binomial distribution. Then we'll discuss the application of binomial distribution in biostatistics. We'll discuss properties of binomial distribution. Then we look at some worked examples. Then look at some exercises to test our knowledge of binomial distribution. And then we finally summarize the module. So I guess we can get started with the Bernoulli trial and the binomial distribution. In theory of probability and statistics, a Bernoulli trial, which people also call the binomial trial, is a random experiment with exactly two possible outcomes, success and failure. Is experiments with only two possible outcomes, not three, not four, not five, only two, success or failure, in which the probability of success is the same every time the experiment is conducted. It is named after Jacob Bernoulli, a 17th century Swiss mathematician who analyzed them in his Ars Conjectandi in 1713. Ars Conjectandi is a mathematical published work by Jacob Bernoulli, a Swiss mathematician. So as the name suggests, Bernoulli distribution is a probability distribution of a single Bernoulli trial, with 1 denoting success and 0 denoting failure. It is the simplest of all probability distributions because it's a single trial, has only two possible outcomes, and we just need to know the probability of getting each outcome. The outcomes in the trial are mutually exclusive. That is, both outcomes cannot occur at the same time. An example is a single toss of a coin. When you toss a coin, you either get head or tails. You can't get both. You can't toss a coin once and then head and tail will both show up at the same time. It's either head or tail. They are mutually exclusive. Both cannot occur at the same time. So the head can be counted as a success, while the tail as a failure, or vice versa. All the trial is clear. It's a single trial with only two possible outcomes, success and failure. The probability of success is the same every time the trial occurs, and the outcomes are mutually exclusive. An example, you coin toss. Every time you toss a coin, as long as the coin has not been probably mishandled, and it's a fair trial, there's a 50% chance always of it being head or tail, and both cannot occur at the same time. Now, this is a pictorial illustration of what a Bernoulli distribution looks like. Here is 0 or 1. And you see that sometimes some Bernoulli trials have different probabilities. This first one describes a coin toss with 50% probability of a head, 50% probability of its tail. The others also have different probabilities. Here, the second one, there's an 80% probability of a failure, which is 0, and a 70% probability, of failure, and a 30% probability of success. But the important thing is that for every trial, success or failure probabilities are the same. Bernoulli is always a single trial. So what if we do multiple Bernoulli trials as part of a single experiment, like Bernoulli trials carried out any number of times? The number of successes and failures in n independent Bernoulli trials for some given value of n is represented by a binomial distribution. So we carry out multiple Bernoulli trials n number of times. These independent Bernoulli trials can then be represented by a binomial distribution, the number of successes and failures. And that is the link between a Bernoulli trial and the binomial distribution. So, with that understood, we go on to the binomial distribution itself. A distribution where only two outcomes are possible, such as success or failure, gain or loss, win or lose, and where the probability of success and failure is the same for all the trials, is called the binomial distribution. The outcome will not be equally likely, but their probabilities must sum up to 1. Remember in the previous slide, we saw distribution of some trials showing their success and probability of their success and failure. And we saw that we had 50-50% probability for success and failure. One also had 70-30 and so on. So the outcome will not be equally likely, but the probabilities must sum up to 0. When you have 50-50, you have 0.5 plus 0.5, which sums up to 1. If you have 70% to 30% probabilities, we have 0.7 plus 0.3, which also sums up to 1. The binomial distribution can be mathematically described as follows. Probability of x, that's probability of the number of successes desired, is equal to n combination x times p raised to the power of x times q raised to the power n minus x, where n equals to the number of trials or the number being sampled, x equals to the number of successes desired, p, the probability of getting a success in one trial, and q equals to 1 minus p, which is the probability of getting a failure in one trial. I'm sure that makes sense. Q equals 1 minus p, probability of success. 1 minus probability of success will be probability of failure. To further break down this formula, n combination x can be written as n factorial divided by n minus x factorial times x factorial. What do you mean by n factorial? It means n multiplied by all the values lower than n till we get to 1. Okay, let's use an actual figure. 7 factorial will be equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial will be equal to 5 times 4 times 3 times 2 times 1. So when we say n factorial, we mean n multiplied by all the digits lower than n up to the value of 1. So the formula further broken down, n factorial over n minus x factorial times x factorial. That division multiplied by p raised to the power x times q raised to the power n minus x. We already know what all these variables mean. That is a mathematical description of a binomial distribution. For a situation, a scenario to be modeled as a binomial distribution, it must follow some specific rules. What are these rules? Rule number 1, there are only 2 mutually exclusive outcomes for a discrete random variable, that is success or failure. Only 2 possible outcomes. Like we discussed, the flipping of a coin, there are only 2 possible outcomes, head or tail, and they are mutually exclusive. Both of them cannot occur. If one occurs, the other cannot occur. So it's flipping of the coin can be modeled by a binomial distribution. Rule number 2, there's a fixed number of repeated trials. That means we can't keep repeating to the infinity. These trials must have an end, so it'll be finite. That means if you have to flip a coin, there will be an n number of trials, maybe like 10 trials. Rule number 3, each trial is an independent events, meaning that the result of one trial doesn't affect the results of subsequent trials. And the rule number 4, the probability of success for each trial is fixed. That is, the probability of obtaining a successful outcome is the same for all trials. If a scenario meets all of these rules, all of these criteria, then the probabilities can be modeled by a binomial distribution. Here we have a plot showing a binomial distribution with different values of P and N. Remember, we said P is a parameter describing the probability of success, while N is the number of trials. So we see that for the blue plot, it describes the binomial distribution when P equals to 0.5 and N equals 20. The green describes when P equals 0.7 and N equals 20. And the red plot is for P equals 0.5 and N equals 40. As P equals 0.5, the binomial distribution is symmetrical. I'm sure you've noticed that in the previous slide. But at lower or higher probabilities, the distribution can be right or left skewed respectively. Here we have two plots. At a lower probability, we can see that the distribution is skewed to the right, as shown here. The distribution is skewed to the right. Here, N equals 20 and P equals 0.1. So it's no longer symmetrical, and the distribution is skewed to the right. So that is what changing parameter P can do to the distribution, the plot, the shape of the plot, binomial distribution plot. At a much higher probability, P equals 0.9, the plot can be skewed to the left, as you can see on this plot on the right here. So we can see that changes in the value of P affects the shape of a binomial distribution plot. So we move on to the application of binomial distribution in biostatistics. How do we apply this distribution in biostatistics? For example, let's say the actual prevalence of COVID-19 in your country is about 1%. The value is not actually known. We don't know the true prevalence. So usually what epidemiologists do is conduct seroprevalence studies in a random sample. We won't go into the details of what seroprevalence studies are. They are not relevant to what we are discussing. But why do we do this study? Because of its utmost importance to get an idea about the actual prevalence of the disease to guide important policy decisions. But it is not practical to conduct this study on the entire population. So they would rather select a random sample of size, let's say 1,000. So a subject is drawn randomly from the population and is tested for COVID-19. This process can be considered to be a Bernoulli trial. Now, when you do this for 1,000 subjects, it becomes a binomial experiment. The number of successes here would be nothing but the number of subjects who tested positive for COVID. You can argue that here the trials are not independent because once a subject got tested, he is not replaced. And hence, this is not a sampling with replacement. Because this is not a sampling with replacement, the probability of getting tested positive is not the same for each subject. Basically, we are saying that the probability of getting tested positive is not independent, it's dependent on previous tests as we are sampling without replacement. However, this criteria can be neglected because the sample is large enough. So this criteria can be neglected with a large enough sample size. And hence, COVID-19 studies or tests or trials, as we call it, can be modeled by a binomial distribution. Other use cases of binomial distribution are if If a new drug is introduced to cure a disease, it either cures the disease, that is success, or it doesn't cure the disease, that is failure. Whether an organism in a given environment will survive or die, survive success, die failure. If there are two possible alleles, uppercase A and lowercase a at a given locus, we want to know the probability that 5 out of 10 children are double uppercase A, where P is the probability of a child being double uppercase A. So these are some other small examples of binomial distribution in biostatistics. Now, the properties of binomial distribution. According to the central limit theorem, the distribution of the sample mean, which is the sum of n independent random variables divided by n, approaches a normal distribution for large values of n. Since the binomial is the sum of Bernoulli random variables, it can be approximated by a nominal distribution. The first step into using the normal approximation for a binomial distribution is making sure you have a large enough sample. How large is large enough? Basically, we are saying that we can approximate a binomial distribution into a normal distribution if the sample is large enough. How large is large enough? We figure this out with two calculations, n times p and n times q. N is your sample size, p is your given probability of success, while q probability of failure. For example, let's say your probability p is 0.6. You can find q by subtracting this probability from 1 in terms of probability q, which is probability of failure, equals 1 minus 0.6, which is equal to 0.4. Percentages instead of decimals can make this a little more understandable. So if you have a 60% chance of it raining, there is a 40% chance that it will not rain. When n times p and n times q are greater than 5, you can use the normal approximation to the binomial to solve a problem. So I noticed an error here, not 0.04. It is 0.4. Good. So when n times p and n times q are greater than 5, we can use the normal approximation to the binomial to solve a problem. The expected value and the variance of the binomial distribution are as follows. The expected value, which is the same as mean, we are talking about distributions, equals to n times p, or the variance equals to n times p times q, or you can say n times p multiplied by the value of 1 minus p, which is same as n times p times q. Those describes the mean and variance parameters of the distribution. So we can see plots of binomial distribution approximated to the normal distribution. If you multiply n times p for each of these distributions, we will see that the values will be greater than 5 as stipulated here. So we can use the normal approximation to the binomial in cases like this. For example, 20 times 0.5 for this red plot is equals to 10, where n equals 20 and p equals 0.5. For this green plot, n equals to 100 and p 0.5. If you multiply them, it gives you 15. So we can use the normal approximation to this binomial distribution. So now we move on to the worked examples. So we see how we can use mathematics to gain a better understanding of binomial distribution. So the first example, a biologist examines frogs for a genetic trait he suspects might be due to contaminated water. Normally, the trait examined presents itself on average in 1 out of 8 frogs in the wild. If the frequency of this trait has not changed and it captures 12 frogs for examining, what is the probability it finds this trait in 3 or more frogs? We know what our formula is, n combination x times p raised to power x times q raised to power n minus x. So we have to plug in what these values are, what n is, what x is, what p is, and what q is. And then we can quickly find the solution to this problem. So from the question, it can be determined that n equals to the 12, because it says that it captures 12 frogs to examine. That means it's going to carry out a trial on each of these frogs. That is n trials, 12 trials on these 12 frogs. Our value of x is equals to 3, because we're trying to find the probability that there's a trait in 3 or more frogs. So x becomes 3. Our p is equals to 1 over 8, because it says 1 out of 8 frogs in the wild, that we find this trait in each of on average 1 out of 8 frogs in the wild. So probability of success equals 1 over 8, which in decimal is 0.125. Q in this case will be 1 minus p. That's probability of not finding the trait in the frog, which will now be 7 over 8 in decimal 0.875. So plugging in the values into this formula, we then be able to find the probability. But there's a caveat. We don't want p with x equals 3. We want p with x equals to or greater than 3. What's the probability he finds this trait in 3 or more frogs? Not in 3 frogs, 3 or more. That's 3, 4, 5, and more. What that means is that this is an infinite number of probabilities to calculate, because we have to find the probability of x equals 3, x equals 4, x equals 5, up to an infinity. That is a rigorous task. So instead, we calculate the probability of finding less than 3 frogs with the trait, and then subtract it from 1. This is known as complement to our probability, similar to how Q is derived from P. So rather than doing P for x equals 3, P for x equals 4, up to infinity, we can just find P for x equals 2, 1, and 0, and subtract it from 1. That will give us probability of P equals P is x equals 2 or greater than 3. Hope that's understood. So we find 1 minus P with x, 1 minus probability of x less than 3, which will be equal to 1 minus the probability of having 0 traits found in the frogs, or 1, of having the traits found in 1 frog, or probability of having the traits found in 2 frogs, or probability of not finding the trait at all in any of the frogs, which is P0. Here we plug in the values, 1 minus this, we plug in, this is our n minus x, that's 12 factorial over 12 minus 0 factorial times 0 factorial times 0.125, which is p is power 0x, times q is power m minus x, which is 0.875, is power 12 minus 0. That's for probability of 0. Probability of 1, we do that, so we plug in the values. Probability of 2, we do that, plug in the values. The difference here is that x changes for each of these probabilities, that is all. Every other thing remains the same except the value of x. So when we get that, we subtract it from 1, and then we get 0.182, which is equals to 18.2%. So that 18.2% probability that the biologist finds the genetic traits in 3 or more frogs. Hope that is understood. The second example. Suppose 23.5% of individuals in a given patient population are HIV positive. If 16 individuals are selected from this HIV population, what are the chances that 8 of these individuals are HIV positive? So we do as we did before. We find the values of n, x, p, and q. From here, we can tell that n equals 16 because we have 16 individuals that are being tested. Our p is 0.235, which is quite stated against 23%, 25% of individuals in the population are HIV positive. So P equals 0.235. Q, 1 minus P, which is 1 minus 0.235 is equals to 0.765. While our X equals 8. What are the chances that 8 of these individuals are testing for X equals 8? We plug in these values into the formula, and then we apply for P with X equals 8. Here is a very straightforward solution, because we're not finding the probability of less than 8 or 8 or greater, 8 or greater, you just find the value of P when x equals to 8. You plug in the values, m here is 16, so 16 factorial over 16 minus 8, which is x, m minus x times x factorial, which is 16 minus 8 times 8 factorial, times 0.235 raised power 8 times 0.765 raised power 16 minus 8, which gives us a probability of 0.014. Therefore, there's a 1.4% chance that 8 individuals from the 16 selected will be HIV positive. So now, with a better understanding of the formula, we look at some exercises. To look at some exercises. There are 2 of them here. They'll be read out, after which you try to solve them. So exercise 1. A pharmaceutical lab states that a drug causes negative side effects in 3 of every 10 patients. To confirm this claim, another laboratory chooses 5 people at random who have consumed the drug. A. What's the probability that none of the 5 patients have a side effect? And B. What is the average number of patients that the laboratory would expect to experience side effects if they choose 200 patients at random? Question 2. Determine if the following situations suggest a random variable with a binomial distribution. The first situation, the number of people with blue eyes in a group of 10 people drawn from a group of 30 people without replacement. Second, the number of bird chirps one can hear in a day if the average number of chirps per hour is 15. Third, the number of each of 3 species of flowers present in the collection of 100 flowers, and the number of 400 subjects taking atorvastatin that indicated the experience a headache. Sorry. They experienced a headache the same day they first took this drug. Secondly, that the number of 400 subjects taking atorvastatin that indicated they experienced a headache the same day they took this drug. So after reading these exercises, we'll give you 5 minutes to go through them and solve them. Take your time. And 5 minutes start, after which we'll look at the solutions to the exercises. Take your time with the exercises. About 3 minutes remaining. Seconds remaining. So I'm sure we are done with our exercise. Now let's look at the solutions, the exercises. Yes, there we go. The solution to question 1. From the question, it can be separated that P equals 3 over 100, which is 0.03. And the question says 3 of every 100 patients experience a negative side effect. So the probability here, P equals 3 over 100, 3 in every 100, which is 0.03. Invariably, that means Q is 1 minus 0.03, which is 0.97. N is 5, because it's the experiment. 5 people are selected for the trial. So we have 5, N equals 5 trials. Yx is equals to 0. Because from question A, what's the probability that none of the 5 patients have a side effect? And what's the probability that we have 0 patients with a side effect? 0. X equals 0. If you plug in these values, P, Q, X, and N, into the formula, which are very familiar with now, this is what we get: 5 factorial over 5 minus 0 factorial times 0 factorial. All of that times 0.03 raised to the power 0 times 0.97 raised to the power 5 minus 0. And that will give us 0.859, which is equals to 85.9%. So there's an 85.9% chance that none of the 5 patients that are selected for the trial will have a side effect. So question B, what is the average number of patients that the laboratory should expect to experience side effects if they choose 200 patients at random? The average number. Here, N becomes 200. And we know what average means. Average can also be the same thing as a mean. So to find the average, we use the mean formula, which is equals to N times P. We already know P as 0.03. And since we are selecting 200 as random, N becomes 200 for this particular question. Question A, it was 5 because we're selecting 5 patients. Now we're selecting 200 for this question. So N becomes 200. And hence the average to be expected will be 200 times 0.03, which is equal to 6. Seems pretty straightforward. Now, question 2. The first situation, we have to determine if the following situation can be described with a binomial distribution. So the situation A, the number of people with blue eyes in a group of 10 people drawn from a room of 30 people without replacement. Is it the binomial distribution? No. The trials, the people drawn from the room and tested if they have blue eyes or not, are not independent. Since there is no replacement, as people with blue eyes are drawn from the room, the probability the next person drawn from the room has blue eyes decreases. So the more people with blue eyes that we draw without replacement, the probability that the next person drawn from the room also has blue eyes decreases because the pool from which you can draw from has decreased. So there is no replacement. If there was a large enough sample size, this might have been neglected. just like the COVID case we discussed when we're discussing the application in biostatistics. But in this case, there are not that many of them. A group of 30 people, so the sample is not large enough, so it can't be described with a binomial distribution. The second, the number of bird chirps one can hear in a day if the average number of chirps per hour is 15. No, there is no upper limit on how many chirps one could hear. In a binomial situation, the maximum number of successes is limited by the fixed number of trials. Now that in one of the rules that were stated, the trials have to be finite. They have to be an end to the trials. It cannot be infinite. But in this case, the chirps, there are no infinite number of chirps that one can. There's no finite number of chirps. It's just infinite. The bird chirps. There is no specified number of trials. So it cannot be described as a binomial distribution. The third situation, the number of each of 3 species of flowers present in a collection of 100 flowers. The number of each of 3 species of flowers present in a collection of 100 flowers. No, that still can be described as binomial distribution because there are more than 2 outcomes. If one species could be the success and another could be the failure, what would the third species be? Remember, we said there can be only 2 outcomes. Only 2, not more than 2, not less than 2. Only 2 outcomes. So this cannot be described as a binomial distribution either. And now the final one. The number of 400 subjects taken atorvastatin that indicated they experienced a headache the same day they first took the drug. Yes, this situation can be described as a binomial distribution. This suggests a random variable with a binomial distribution. There is a fixed number of subjects or trials and only 2 possible outcomes, headache or no headache. In this case, depending on the context, you can call headache the success and no headache the failure. There is a fixed number of subjects of 400 and there's a defined mutually exclusive 2 outcomes, headache or no headache. From these exercises, we understand how to apply the formula for binomial distribution and what type of situations can be modeled with a binomial distribution. So, if you didn't get any of those right, not to worry, your practice makes perfect. So just go over them again and try working those examples, those exercises, and seeing how you can improve. So now we're going to summarize this module in our summary section. So we have 3 key takeaways from this module. The first key point says, for trials to be modeled as a binomial distribution, they must meet certain criteria. First, there are only 2 mutually exclusive outcomes, success or failure. Second, there's a fixed number of repeated trials. That means you can't have infinite number of trials. The number of trials, n, must be finite. So each trial is an independent event. That means one trial does not affect the outcome of the following trial or others. And fourth, the probability of success for each trial is fixed. I mean, it is the same, it does not change. The second key point, a binomial distribution can be approximated to a normal when the sample size is large enough, such that n times p and n times q are greater than 5. That means if your sample is large enough, such that when you multiply the product of the number of trials times the probability of success is greater than 5, then the binomial distribution can be approximated to a normal. The mean of the binomial distribution is n times p, number of trials and the probability of success. Now the standard deviation is the square root of the product of n, p, and q. The third key point, a binomial distribution can be mathematically described with the equation n combination x times p raised to the power x times q raised to the power n minus x, which is equal to n factorial over n minus x factorial times x factorial, all of that multiplied by p raised to the power x times q raised to the power n minus x. That has stated in this image, where n equals the number of trials, p the success or probability of success, q the probability of failure, and x the expected number of success. Those are the three key takeaways from this model. Now, some references are stated here, so we can see how far back this school of thought in binomial distribution has taken place. You can see that the first reference by Wandsworth GP was published in 1960. That's the Introduction to Probability and Random Variables. We also have another one by Robert Dennis, Demystifying Binomial Distribution. It was posted on the Towards Data Science website on the 5th of July 2020. We have some other references also listed out here too. So you can go through them and to brighten or improve your knowledge or increase your knowledge in binomial distribution. This is where we come to the end of the module. Thank you very much.